Swayam Prabha. Digital India. Educated India.
Welcome to lecture 2. Okay, so this we are going to do a recap of the thermodynamics first, and after we do the recap we will try to see that what is relevant in the multiphase systems. So let us start with the problem that let us look at a single component closed system. Okay. Now, in the single component closed system, okay, what can we say about the first law of thermodynamics? So, the first law of thermodynamics basically is okay. So, in this particular this term is basically the heat transferred, this term is basically the work done by the system, and this is basically the total energy. Total energy, this includes the internal energy. So, this is the first law that you know for any single component closed system, right. So, as we can see from this particular expression over here, the change of thermodynamic properties depends on the initial and the final states only and not on the path. So, this we already know that the change of thermodynamic properties depends on the initial and final states only and not on the path. This you already know, but however, quantities like dq and dw, okay, are path dependent. So, that is why we have written them by that tilde kind of a symbol, right. Okay. And in most cases the work will be basically the mechanical work, which is basically PdV. This is the mechanical work for closed system. Okay. So, this is the first law of thermodynamics for any closed single component closed system. Okay. This we already know, and we already know about these features, that this is path dependent, the internal energy is basically path independent and all those things. Okay. So, going to the next page, the second law of thermodynamics, let us look at. So, we have looked at the first law. The second law of thermodynamics okay, again for a single component closed system. Okay. Let us look at that. In that particular case, as if you recall the second law, okay, the Clausius inequality. Okay. So, the equality sign is greater than equal to, right. So, the equality sign, as we know, equality sign corresponds to the reversible process. This is what we all know, right. Okay. So, if we combine the first and the second law, first and second law, okay. So, if you combine the first and the second law to determine, basically the purpose of this is to determine the stability and equilibrium okay, of a system. Okay. Now, in that particular case, okay, if you combine these two and neglecting the non-internal energy parts, you can write it like this, ds minus w. Okay. So, this particular thing combines the first and the second law of thermodynamics essentially. Now, for a finite change, so this is for infinitesimal change. For finite change, okay, we have where w is basically nothing but the integral from 1 to 2, whatever is the process, okay, p dv. So, that is the mechanical work, that is the work done by the system to surroundings, by system to surroundings. Okay. So, this is the second law and the first law combined, we get this, right. And we have also seen that if we, this is an inequality statement, because the second law, as we know, that is also an inequality statement in itself. Okay. So, now these are all for single component systems. Okay. Now, let us look at one more important parameter over here, which is basically called the Gibbs phase rule. Now, what is Gibbs phase rule? Gibbs phase rule basically identifies the degree of freedom, and we will come in a second what degree of freedom means. Degree of freedom of a multiphase system okay, that is in thermodynamic equilibrium. Okay. So, the Gibbs phase rule is basically identifies the degree of freedom of a multiphase system that is in thermodynamic equilibrium. Okay. And it basically what it tries to also do, okay, is that it tries to relates the number, this is number of intensive independent thermodynamic properties okay, for each phase. Okay. The number of intensive independent thermodynamic properties for each phase and the number of phases of a system. This is not coming, and so we move on to the next page. So, it basically relates the number of intensive independent thermodynamic properties for each phase and the number of phases for a system. So, in an equation form, if we have to write, this will be something like this, n plus 2. Now, what are each of these things? this is the number of phases, this is the degree of freedom, this is the most important thing. Degree of freedom, okay. These are the number of components. As I said, multi-phase system can also be multi-components, okay, number of components of the system. So, F is basically, by degree of freedom, what we mean is that F is the number of intensive, mark the words, number of intensive independent variables, okay, or independent properties that must be specified to fix the state of the system for each phase. So, that is a very clear cut indication that what we mean by the degree of freedom. The degree of freedom essentially means the number of intensive independent properties that must be specified to fix the state of the system for each phase. Okay. So, let us say for pure substance, let us take some examples. For pure substance, that means single component, single component, it can be of course of two phases also. For single pure substance, n is basically equal to 1 because the number of component is equal to 1. For single phase, this is equal to 1 because the number of phases is equal. Okay. Now, let us take an example of a pure substance, that has two phases in equilibrium. Let us take this as an example, a pure substance which has got two phases in equilibrium, okay, like for example a saturated liquid vapor. This can be water and water vapor, for example. That is the easiest example that you can think of. In those cases, this is equal to 2, n is equal to 1, leads to the degree of freedom is equal to 1. So, that implies that only one intensive independent property needs to be specified to determine the state of the system, correct. So, pure substance which has got two phases, here it implies that if F is equal to 1, only one intensive independent property is needed. This would imply that for such a system, if you specify P, which is basically the pressure, right, temperature is directly known. Right? Isn't that what happens actually in a thermodynamic system as well? If you recall the vapor pressure dome, right, you would find that in the saturation region where liquid and the vapor are existing in equilibrium, you will find that you just need only one property to specify. The temperature and the pressure are not two independent properties in that particular case, right, and that is why you have a saturation pressure, saturation temperature kind of a table. You can look it up, right. So, there is a unique, these are like unique combinations, correct. So, the temperature is directly known because the Gibbs phase rule actually states that only one is actually needed. However, we do not know the relative abundance of each of the phases. That means, if you have heard the word quality, quality means what is the fraction of liquid or vapor, right. What is a quality? Quality means what is the relative fraction essentially. So, this is relative fraction of vapor and liquid. Now, the relative fraction of vapor and liquid, if you say, if that is not known, in many cases it may not be known, right. So, in that particular case you do not know the relative abundance, but you can definitely know that if you specify temperature, the pressure is known. So, you just need one thermodynamic parameter to specify this. So, if you look at it basically in a chart like this, right. So, this is the portion that you all know is basically the two phase region, right. Now, in this two phase region, as you can see, the pressure and the temperature, they are interrelated to each other, but however, as you move from this side to that side, the quality actually changes. There is less amount of water vapor to more amount of water vapor. This is like any saturation chart will actually show you that. Okay. So, I think this part is quite understood, that the Gibbs phase rule gives an important tool to basically calculate that what is the number of variables that you need, and this would be vitally important as we move, as we will see in the later part of this particular course. Okay. Now, where did the mouse go? Okay. So, now in the remaining time that we have, let us look at the equilibrium and stability of single phase closed system. So, equilibrium and stability of single phase closed system. Okay. So, there are several possible ways. One is basically if you assume that the system is of constant volume and isolated. From your previous knowledge of thermodynamics, you already know what a constant volume isolated system can be. If you consider the system as constant volume, constant temperature, system, the system can be also of constant pressure, constant temperature. Okay. So, there are, like, we will see three possible systems over here. Okay. So, the first one, which is basically a constant volume isolated system, let us look at that. In that particular system, as you know, because it is isolated, the net heat that is transferred is basically 0. Okay. And it is a constant volume. So, the net volume change is also equal to 0. The work that has been done by the system is also equal to 0. So, these are the three things that we know that it is true. From first law, what else do we know? From the first law, we know that the change of internal energy of the system is also equal to 0, correct? That is because it is an isolated system, right. So, from second law, we can tell that the change of entropy of the system for constant energy, internal energy and constant volume should be always greater than equal to 0, correct. Okay. So, the system entropy, this proves that the system entropy for this isolated constant volume system, the system entropy always increases for spontaneous, okay, irreversible finite processes. Got it. So, that is very obvious that the entropy always increases. So, if I look at this, the entropy always increases for a system which is constant volume and isolated, and the if the process is spontaneous and irreversible, that is the important word, and finite, then the system entropy will always increase. So, that is the stability criteria for a constant volume isolated system, right. Okay. So, let us look at the stability criteria for a constant temperature and volume system. So, a constant temperature and volume system, if we have volume system, if we have. Okay. Now, in that particular kind of a system, what we have is that delta T is equal to 0, because it is a constant temperature. The volume is also equal to 0, that is a constant volume. If the work is PVB type, if work is of PV type, that is mechanical work, then W is also equal to 0, correct, because there is no change in volume. Okay. So, therefore, your change of internal energy and the change of entropy must be less than equal to 0. Okay. That is a relationship that we can say. Also recall that F, we will come to the see what F is. F is basically nothing but the Helmholtz free energy, right. This you know from your undergraduate thermo. Helmholtz free energy is given by this particular expression, right. Okay. So, if I apply, so if I just basically see the change in Helmholtz free energy, that is basically given by delta E minus T delta S minus S delta T. Now, for this particular process, this is of course equal to 0, because it is a constant temperature system. So, this is the relationship that is valid. So, substituting this over here, right, what we get as a result of that is delta F, that means the change in Helmholtz energy for constant temperature and constant volume must be less than equal to 0. Okay. So, the Helmholtz free energy must decrease. See, entropy was must increase for an isolated system, must decrease with any spontaneous system change and is minimal at equilibrium. Okay. So, that shows basically the Helmholtz free energy must actually decrease, okay, for a constant temperature and a constant volume kind of a system, and this we have just used the first and the second law of thermodynamics for this, right. Okay. So, similarly, and this would be the last thing that we will do for constant temperature and pressure system. Okay. What we have, that was a third system that I said, delta T is equal to 0, delta P is also equal to 0. So, the only work is done of PVB type, once again type. So, the work done is basically P into delta V. Remember here the volume constant is not there. Okay. So, it is a constant temperature and constant pressure system, right. So, just by using these two expressions we can see TdS plus P delta V is less than equal to 0. So, that is the first and the second law combined, correct. Okay. Now, recall once again now, like you recalled Helmholtz free energy at that particular point, recall Gibbs free energy now. Okay. So, what is Gibbs free energy? G equal to E minus Ts plus PV. So, the change in Gibbs free energy will be given by delta, sorry, will be given by delta E minus S delta T minus T delta S, okay, plus P delta V plus V delta P. Okay. Now, of course, this is equal to 0, this is also equal to 0. So, the Gibbs free energy is basically therefore given as delta E minus T delta S plus P delta V, which is basically the same as this. So, I substitute it over here, right. So, and we get the expression that the change in Gibbs free energy for constant temperature and pressure must be less than equal to 0. So, the same statement holds that the Gibbs free energy must decrease like the Helmholtz free energy for a constant temperature and pressure system. Okay. So, these are one of the 3 main equilibrium statements that we will make for 3 types of systems. Okay. So, we will end lecture 2 kind of here, and we will take up we will move forward to the 2 phase part of this same thing in the next lecture. But however, remember that the equilibrium constraints therefore are given as delta G T P less than equal to 0, delta F T V is also less than equal to 0, delta S E V is less than equal to 0. Okay. Similarly, you can show it for other types of systems as well, okay, and we are not going to do that, but we can show the other equivalent statements. That means, sorry, we can show that delta E, that is the change in internal energy comma V, is less than equal to 0, delta S, okay, or rather sorry, delta H S comma P should be less than equal to 0. So, these are also equivalently other systems that you can prove that they also follow a similar type of framework. So, all the systems, the stability part can be represented in this kind of forms. Okay. So, we will see in the next class what happens afterwards. Okay. So, this is the end of lecture 2, and we will meet you next in lecture 3.